So, on behalf of Professor Causal, let me introduce the speaker. This is Professor Rahul Mukherjee, and just because I don't want my introduction to be longer than his talk, let me just say this, that almost any award in statistics that you can get, he has got. Membership of committees, you name it, is there. He has visited now about 18 universities, 6 in the US, 3 in Japan, 5 in China, and he is part of the editorial board. He is or was part of the editorial board of a whole bunch of journals. So I'm not going to say all of that about him. One thing which you may not know is that he has also been a teacher to several people here. For instance, Professor Causal, me, Professor Karthik Sriram, Professor Kirti Sharda, Professor Sarad Mukherjee, and a whole bunch of people. So without taking any further time, Professor Mukherjee, and public. So without taking any further time.
Thanks so much, Nitish, for your kind words, and thank you very much for your kind invitation. In particular, Tathagata, for your kind invitation. And I am so very happy to be here at this very distinguished seat of learning. Thank you very much. So, well, causal inference and finite population sampling. Let me start with one example, and this example relates to gross human rights violation. Forewarning, don't accuse me of such human rights violation. That dates back to 1943, 44, 45. The Japanese occupation of China, northeastern part of China. Those of you who are interested in history may recall that we draw the map of China, a very rough map. This is, well, again, there can be something debatable about the Indo-China border. I am not entering into that. Far away from the Indo-China border, I will concentrate on this region, which we call Manchuria. The Chinese hate that word because Manchuria sounds like Manchukuo, the puppet state that the Japanese established during the Second World War. Many of you, I'm sure, have heard of the film, or maybe have watched it, The Last Emperor, which dwells on Wu Yi, who was the last. Well, the Japanese revived the Qing dynasty over there, and Wu Yi was the puppet emperor. The capital city here in the Jilin province of China, that was, the Japanese called that, I think Xinjing. Xinjing means the new capital, and the Chinese changed the name to Changchun. Changchun means the land of eternal spring. A little north of these, here, there is a place of great touristic interest, which is called Harbin. Harbin. And Harbin is the capital of the Heilongjiang province of China. Heilongjiang means the Black River. Black River, what Black River? Farther north of it flows a great river that empties itself into the Pacific, and you know the name, it's Amur in the map. The Russians call it Amur, the Chinese call it Heilongjiang. And this is a no-go region for us. I could travel only up to this point, Harbin. And near Harbin, some gross human rights violation was perpetrated around 1943-44. In the suburbs of Harbin, somewhere here, this part is Inner Mongolia Autonomous Region, and this part is Manchuria. But don't say Manchuria to Chinese. They call that Dongbei. Dongbei means east, north, east, north. We say northeast, they call it east, north, Dongbei. So this is the capital of the Heilongjiang province called Harbin, and Harbin has many places of significant touristic interest. I went there primarily for that, the Russian architecture, the river, the train going all the way to Vladivostok, all such things are there. Great place. And old-fashioned hotels, cobblestone streets, all such things, and also some memorabilia of the early Communist Party meetings there. Now, near Harbin, there is a place, there is a research center established by the Japanese in those days. So, you know, the Japanese used to do all sorts of experiments with their prisoners. So, let me narrate one such experiment. So, this is the prisoner standing here. Fine? The experiment goes like this. You apply pressure on this prisoner in this direction. Fine? And see at what pressure this person dies. And there is, with another prisoner, the experiment could be you apply pressure in this direction and see at what pressure this prisoner dies. Fine?
This is given near the air or what? How do you do that?
So physical suppression. Okay. This is X say, and this is a Y. Then there comes, well, I do not think that they did exactly this experiment. They did something similar. Because you know, these are all shrouded in mystery, and the Japanese destroyed our fights near the end of the Second World War. So this is called X, the vertical pressure. This is called Y, the horizontal pressure. So they measured X for some people, they measured Y for some people, and then comes the big question: how to find the correlation coefficient between X and Y? Don't worry about correlation coefficient, the connection between X and Y. In plain language, how are X and Y related? So correlation coefficient is a measure of this relationship. I suppose everyone here knows the formal definition of correlation coefficient. At least everyone should remember that in order to get the correlation coefficient, I must get these pairs xi, yi, I equal to 1 to n with n people. Then I can calculate the correlation coefficient using a formula. Don't worry about the formula. But I require xi, yi, I equal to 1 to n. Can you get the correlation coefficient here? No. I apply pressure in the vertical direction, the person dies. Then how can I get y? And here, for some people I get y, but not x. So I cannot get pairs. How do we get the correlation coefficient? I cannot. So from here, the story begins. So we have data. We have data on xi for I equal to 1 to n1, and we have data on yi for I equal to n1 plus 1 up to n. Correct? I do not have matched data. From these, can I get the correlation coefficient under some assumption? However strange that might be, we can. And there comes the notion of strict additivity. Strict additivity. In its simplest form, strict additivity means xi minus yi equal to constant over I. This is called strict additivity. There can be various forms. Instead of xi minus yi, I can take alpha xi plus beta yi equal to c, where alpha and beta are known constants. Can we get the correlation coefficient then? Start from here. Right hand side is a constant, so its variance is 0. And what about the variance of the left hand side? Vx plus Vy minus twice cos xy. Is this clear to everyone? This statement? My dear fellowship students, this is clear to everyone, irrespective of your background? Now, from here I can get cos xy equal to Vx plus Vy by 2. Can we now estimate Vx from this data? Yes, we can, provided N1 is greater than 1. Can I estimate Vy? Yes, provided we have the number of Y readings is at least 2, we can do that. Then we can estimate convex Y. Then from there I can estimate the correlation. So this is the starting point of the research that we are talking about here. So this xi and yi, these are called potential outcomes, Y's. I have altogether n people. On each I could measure either x or y, but not both. So I take a random sample of people on whom I measure x, and in the complementary set I get y. So I read the potential outcome x on one part of the population. Well, here the entire set of results to be the population, and in the complementary set I get the reading of y. And from that I can talk about the covariance under assumptions of this kind. So this, for each unit, theoretically I have xi, yi. These are called potential outcomes. On some I observe only xi, on some others I observe only yi. These are called potential outcomes, and we can talk about estimating the covariance, or more generally, variances of linear combinations. Those will also involve covariances under assumptions like strict additivity. Here comes one more question. Strict additivity is rather too demanding. Can we do something under less stringent assumptions? So this talk is in that direction. And well, there are examples abound. For example, say in a class there are say 50 students and say 5 methods of instruction. So one method of instruction is applied at random to 10 students, the second one to another 10, third one to another 10, and so on. Then for each student there are 5 potential outcomes depending on the method of instruction that the student is exposed to. But we are reading only one, we are measuring only one. So from this, can I compare the various methods of instruction? Indeed I can. For example, I have, so this is my universe of the students. I split this at random into 5 sets, S1 union S2 union S5. These 5 are disjoint sets, random sets. This partition is a random partition. Then over S1 I apply one method of instruction. From that I calculate y1 bar ops. That means the first method of instruction, the potentials there from as observed and their arithmetic name. From this I observe y2 bar ops. Now suppose the question is the first method of instruction more effective than the second method? Then I can base my inference on y1 bar ops minus y2 bar ops. Let me repeat. y1 bar ops means the average observed outcome of those people who were subjected to the first method of instruction. y2 bar ops is the average potential outcome, not potential anymore, actually observed outcome of those people who were exposed to the second method of instruction. Then y1 bar minus y2 bar, both observers, can measure the difference between the two methods of instruction. But we are not happy with this difference alone. The next question is how dependable this measure is. And for that, we require the variance. And the variance will again depend on the whole population. It depends on which subset S1 is or which subset S2 is. So that depends on the whole population. That we don't know. Then we have again to estimate that from the data. That means we have to estimate the covariance between these and these from the data itself. And that is not possible because there is no single student who is simultaneously subjected to method of instruction 1 and method of instruction 2, just as no single person was subjected to vertical and horizontal pressure simultaneously. So this is a rather old area of research dating back to 1923, even before the Japanese did their human rights violation research, 1923 by Neymannian. This was published in the Polish language in 1923 and then reprinted in 1919 in Statistical Science, and then Neymannian advocated a principle which is akin to the one that we introduced earlier, like xi minus yi equal to constant, and that principle is called strict additivity. Again, the question is, so, well, even beyond such disastrous experiments involving gross human rights violation, there are applications where these ideas can emerge. And these are applications, right now I give you one example, education, well, in medicine also. Well, there can be a group of people and various medicines can be tried in them, then sociology, psychology, various fields this can be applied. One more point to which I would like to draw your attention. Many of you, I am sure, are familiar with sampling theory. Say, there is a class of students. I want to know, say, the average height of the students in the class. I don't have the time to measure the height of each and every individual. So I pick up a random sample and measure the heights of the people in the sample, and then take the sample mean as an estimation of the population mean. This approach has a similarity with that too. There, in sampling, you pick up one subset at random from the population. Here you are partitioning the population, you are considering a random permutation of the population itself, and you are not happy with just one subset. The first subset applied to treatment 1, that is method of instruction 1. Second subset applied to treatment 2, that is method of instruction 2, and so on. But then, certain basic concepts of sampling theory can be applied here too. Like in sampling theory, the kind of sampling that we talked about is the simplest one, that is called the simple random sampling. There can be other kinds of sampling. For instance, stratification is possible. There can be two-stage sampling and so on and so forth. And the properties, the theoretical properties, ultimately leading to the level of dependability of the estimators obtained from such sampling, depend critically on two things. These are called the first and second order inclusion probabilities. What are these? First order inclusion probability means what is the probability that a particular unit will come to the sample. Second order inclusion probability means what is the probability that both unit I and unit j will come in the sample. And ultimately the properties of the estimators depend on these two probabilities, first and second order. You see the same concept comes here. What is the probability that unit 1 will receive method of instruction 1? That depends on the kind of partitioning that we are using. There we are taking one sample at random. Here we are considering a random partitioning of the population. So the question is, what is the probability? Say unit, now say I am a unit. What is the probability that I will get the method of instruction 2? Fine? Or say, I am one unit and he is another unit. What is the probability that I will get method of instruction 2 and he will get method of instruction 3? These probabilities finally determine all these things. Fine? Of course, there is one problem here that complicates matters. When I am talking about two units, I am implicitly assuming that these two units are distinct. If I talk about the same unit, suppose unit number 1, I am unit number 1. Say, what is the probability that I will be simultaneously exposed to method of instruction 1 and method of instruction 2? What is that probability? 0. Just as no person can be subjected to simultaneously the vertical and horizontal pressure. That complicates matters. Because of that reason, on no individual you can read both the effect of method of instruction 1 and method of instruction 2, which is why the variance estimation becomes so hard. This is the starting point again of the contents of this talk. In 2015, I was visiting my former student, Tirthakar Dasgupta, at Harvard, and then he showed me a paper of theirs that was published in a very nice journal. This is Dasgupta, Pillai, and Rubin. This came out in 2015 in GRSS B, Journal of the Royal Statistical Society, Series B. So Tirthakar showed me this journal and told me that probably there can be much that can be done here. And after I read the paper, it came to my mind that the context of this paper is sort of equivalent to what one does in simple random sampling without replacement in sampling theory. The next question is, in potential outcome models, you do not always have simple random sampling. There can be various kinds of sampling. For example, in methods of instruction, when we talk about methods of instruction, there can be analogs of two-stage sampling. First, you administer the methods of instruction across school districts, and then within each school district, you allocate across teachers. So this is like two-stage. These are called split plot experiments in experimental design terminology. So it came to my mind that probably given the rich theory, the rich unified theory in surface sampling that we already have, can that be applied to the potential outcome models, leading to some sort of unification of the theory there and possibly relaxing this condition of strict additivity. Instead of demanding strict additivity, can we do the variance estimation under milder assumptions? Fortunately, it came out that the answers to both these questions are in the affirmative, and this talk dwells on that. Remote control, we have to go there. Okay, thank you.
Can I ask you a quick question?
Yes, please.
So I'm a bit confused. When I say xi is equal to yi plus constant,
Yes.
the correlation is 1. What are we estimating? So if xi minus yi is a constant.
Very good point. I started with correlation because people think about correlation. My objective is not exactly the correlation, but covariance. Covariance. Because finally, here again, my objective is to find the variance. Variance involves the covariance, ultimately the covariance estimation, not the correlation. I talked about correlation because that's a more popular terminology, which is why I said that. I meant covariance, really. Okay? Now, okay. Got it. Okay, thank you. So causal inference and potential outcomes framework. The setting is that of a finite population, like class of students. Causal inference of treatment contrast. What is treatment contrast? Y1 bar minus Y2 bar, or Y1 bar minus twice Y2 bar plus Y3 bar. That means the sum of coefficients is 0. Applications. There are some references, Invents and Rubin, Cambridge University Press. It's a book, very nicely written one. Then Dasgupta et al., the one that I just now mentioned. Then the highlights. Integration with finite population sampling to develop a unified theory. Then we considered a general assignment scheme. Prior to this work, most of the theory considered analogs of simple random sampling where all possible partitions have the same probability. That is not needed here. Then general linear unbiased estimators, not just the sample mean. Something more than that is possible. There is some reason for considering that. Later on we will see that. Then unbiased estimation of sample variance under conditions milder than Neymannian strict additivity. This is exactly what I was talking about. And then consequences of departure from such conditions. What happens if these conditions don't hold? Then we have to bring conditions like minimaxity or minimum average variance. This covers general factorial treatments. Factorial everyone understands here, like method of instruction versus teacher, or man versus machine. Two factors or multiple factors. And then optimal inference strategy. There is some debate here. There is an open problem and there is some debate, which is why we didn't pursue this setup. Now comes some mathematical symbols. Well, Z is the set of treatments. Like if there are 5 treatments, then Z is 1, 1, 1, 2, 5. If there are 2 factors, one at 3 levels, say in an industrial experiment, so one is, say, or say in an agricultural experiment, suppose plowing in one direction and irrigation in another direction. There can be 3 methods of plowing and 3 methods of irrigation. Then there are 9 treatments altogether, 3 square, which can be written as 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, and so on. So we kept the notation general. Z is the set of treatments. Population of n experimental units. The design assigns each unit to one treatment in Z. This is very important. One, not more than one. No person can be subjected simultaneously to the horizontal and vertical pressures. One treatment in Z. YIZ is the potential outcome of unit I if assigned to treatment Z. So we are observing for any given I, we are observing YIZ for only one Z. For only one Z. And Y bar Z is the average of all potential outcomes. This is not known. This is not known. Because not all units would be subjected to only the treatment set. Then the very purpose of the experimentation would be defeated. Not everyone, not all students can be taught by method of instruction 1. Then methods of instruction 2 and 3 are just untested. The treatment contrast for unit I is summation Z belonging to big Z well. Let me explain the notation. YIZ is the suppose there are 2 treatments, then I have YI1 minus YI2. This is the contrast. This is the contrast for unit I. This is the contrast for unit I. Here the notation goes like this. Z varies over the set 1 to 2 and G1 is 1, G2 is minus 1. G2 is minus 1. So this is the contrast for the ith treatment. Even this I cannot measure because no unit can be subjected to both 1 and 2. And then the arithmetic mean of these over I is the contrast over the whole population. It is here that we are interested. The object of interest is the arithmetic mean across all the contrasts. Okay, now I think I can proceed a bit fast because the rest of the talk, much of the rest of the talk is highly mathematical and probably that would not be of substantial interest. Let me highlight only the key ideas without explaining the notation and all these things in full detail. Only the major points. Intuition. Each y bar z. What is y bar z? Y bar z. Y bar z is the mean. Is the mean of the potential outcomes for treatment z, a particular set. It is the population mean. So in surface sampling, how do I estimate a population mean? Just the sample mean could be an estimate. So intuition provided all units have the same probability of being included. Else it is not. Suppose I am very partial to myself. I include, suppose there are 2 units, I and he. I am very partial to myself. My inclusion probability is 80% and his is 20%. Then the sample mean will not be an unbiased estimator. Okay? So all inclusion probabilities have to be identical. There is one sufficient condition. So, intuition says that each y bar z is the population mean, so estimated by its observed counterpart, that is sample mean, from outcomes of units assigned to treatment set. So tau bar can also be estimated, say, by tau hat bar. What is tau hat bar? Tau hat bar means in tau bar, in the last line, you replace y bar z by its estimate. The intuition tells us how to do that. And in most of the past papers in this area, it was done exactly like this. The challenge, how to estimate the variance. This we go back to square one. Y1 bar ops minus Y2 bar ops. The variance we cannot estimate. Need to estimate the covariance, and it is hard because we observe Yiz for only one z. A key to the difficulty in estimating convex one, the point that I was stressing on right from the beginning, where only one of x and y is observed from each unit. So there is a link with sampling theory that we talked about. Their sample is a subset of the population, and here the population is partitioned into disjoint subsets, and each treatment is assigned to one such treatment. This can help in general assignment schemes. It is at this point that our notation will become heavy, because now we link this, we start linking this with the so-called unified theory of surface sampling, using not just simple random sampling, but using first and second order inclusion probabilities. Every step there has a counterpart here. We try to explore that. At this point of time, I can say very proudly that Indians made a very significant contribution to this unified theory of surface sampling. For example, people like V.P. Godambe, J.K. Rao, Desraj, Murthy, and my own teacher, Professor Arvind Chaudhary, who is still with the Indian Statistical Institute, made very significant contributions to this unified theory of surface sampling. I must also acknowledge with deep gratitude what I learned about this theory from my own alma mater, the University of Calcutta, under the tutelage of my revered professor S. Sengupta, who is no more, very unfortunately. He passed away last year. So in a sense, this talk is my tribute to him, my revered teacher, Professor S. Sengupta. Under whose tutelage we learned all these things. And my task was to integrate what my teacher taught me with this newly emerging theory of potential outcomes. Fine? Now, hereafter, 35 minutes gone. So in another 10 minutes, I will not take more than 10 minutes. Let us have a quick look at the slides I will not try to explain this. By the way, the paper, well, much of the contents of this talk has been published in JASA, Journal of the American Statistical Association, in 2018, and a follow-up paper on the split plot came out in the Annals of Statistics, again in 2018, but some parts of the talk near the end are not yet published. We are working on that, and there are some debates also on some parts. So if you are interested, maybe you should first go through the JASA paper 2018, and there you will find all the details. And when I write papers, I try to be make the paper as brief as possible. Tathagata knows that very well. We work together. These days, it seems that because of print journals are getting obsolete, so the editors don't insist on that kind of drastic shortening. Probably, this runs over about 14 pages in JASA and big pages. If I had free hands, probably I would have reduced this to about 7 pages, keeping the proofs or the major steps of the proofs. But my co-authors were not very happy with the idea, nor the reviewers. So ultimately, it became a 14-page paper. So hopefully, we'll get all the details there.
Then no one will understand.
Tathagata knows my way of writing. Because, in our times when we grew up, print publication was very important, and there were people, for example, the then editor of Biometric, again a top journal, Well, he was always insistent on making the paper as short as possible, So we grew up in that atmosphere. These days it seems that people write long papers. Okay, now quickly, let me finish this. General assignment scheme, the T is the random partition of the population, 1 to n. That means the states, Tz, these are random. Tz are analogous to what we call here S1, S2, S5. S1 is a random part, not necessarily a simple random part. S2 is a random part from the rest, and so on. So Tz is a random partition of the population. Select one Tz with probability Pt. We are not saying that these probabilities should be identical, Pt, greater than or equal to 0, and assign the units in Tz to treatment Z. That means we partition the population as many parts as the number of treatments. Partition is being done at random, and one part is assigned to one particular treatment, and so on. Sigma Pt is obviously 1. Sum of all partitions has to be 1. This covers complex assignment mechanisms such as stratified, split plot. We just now gave an example, fast according to school districts and then according to schools and teachers. Split plot, and then there is unit cluster. Unit cluster is a notorious sampling design. I'm sure you have heard of systematic sampling, which is done for simplicity. In systematic sampling, suppose the population size is 100 and my target sample size is 5. Then I pick up one unit at random from 1 to 20 and then go on selecting the every 20th unit. This is called systematic sampling. The trouble with systematic sampling is that some of the second order inclusion probabilities can be 0. For example, if I pick up one unit from 1 to 20 and then go on selecting every 20th unit, then 1 and 2 can never come together in the sample. Some of the second order inclusion probability is 0, and that entails the same difficulty in variance estimation as we encounter here. More generally, we have unit-cluster sampling designs. Unit-cluster means you have partitioned the population into clusters, disjoint clusters, and pick up one cluster at random. Then again, you can easily see that some of the second order inclusion probabilities have to be 0, so unbiased variance estimation is not possible. Unit cluster partitioning has its counterpart here too, and one can show that if I go by unit cluster, then under no assumption we can estimate the variance here. Under no assumption. So the same difficulty goes on here too. That establishes the one-to-one correspondence between the unified sampling theory and the kind of unification that we are trying to do here even stronger. Next, covers complex assignment. Assignment probability is the first two orders. We talked about this, and clearly you see pi I z z star. That means the probability that unit I gets both treatment z and z star is 0. That complicates matters. Then we talk about linear unbiased estimators. The simplest example of linear unbiased estimator is just a sample mean. Sample mean, is it not linear in the sample observations? And all coefficients are identical. But we can have even more general estimators. Those of you who are exposed to unified theory of sampling will immediately recognize the correspondence between general linear unbiased estimators. In fact, Professor Godambe did a lot of work on these linear unbiased estimators. Then we talk about the estimator of a treatment contrast. So, estimator of treatment contrast is simply y bar hat z. Y bar hat z is no longer the mean, it can be any general linear unbiased estimator. Then we work out its variance. The variance takes such a nasty form, but not really very nasty, it's a quadratic expression. Ultimately, a quadratic expression, the coefficients are nasty. Then comes, probably we can skip this, the main Hartley variance estimation comes here in tau bar square. You see, how does this tau bar come? Tau bar comes, okay, the variance, what is variance? Variance of x is expectation of x square minus ex whole square. So expectation of tau bar hat is just tau bar. So ex whole square is tau bar hat square. That creates a problem. That involves product terms like yiz star. This I cannot estimate because unit I cannot simultaneously get treatment Z and Z. There comes the problem because of this power square. Now, way out is Neymannian variance estimator, which is conservative. Well, Neymannian variance estimator wanted to show that if I make assumptions of that kind, xi minus yi equal to constant, under that assumption, this estimator is unbiased. If that assumption doesn't hold, then it is conservative. That means it has a bias which is non-negative. Non-negative bias is not as bad as a negative bias, because when you estimate a variance, what is the purpose of estimating a variance? It gives you a measure of dependability of the estimator. If the variance is large, then the estimator is not dependent. If the variance is small, it is dependent. Now suppose the true variance is 5, and I estimate that by something that has expectation 6. That means using that estimator, I am always a bit conservative. The estimator, if I say that the variance estimate is 6, and whereas the true variance is 5, then I am not at least giving a misleading picture. If the true variance is 5 and I say that when it is 2, then I am misleading my client, correct? So, a non-negative bias is not too bad, provided it is not prohibitively large. If you are too conservative, well, it comes like this. Suppose a student comes to me, maybe the students will like this example. Say you come to me and ask me to predict your score in an examination. Okay? So, I'll get score in an examination. I will say, if I say that, what is the conservative here? Here a downward bias is conservative. I said that I think you are going to get well around 70 and you eventually get 80, you are not unhappy with me. And if I say that well you are going to get 95 and you get eventually 80, then you are quite unhappy with me. At the same time, if I say that well you are going to get at least 0, then I am very conservative, but you are not happy. Because the bias is too large now, even though I am conservative. So being conservative is not too bad, but being too conservative is non-informative. Correct? Everyone happy with this example? So conservative is good, but only to some extent. So how conservative it is? The next question is that. Okay, way out is Neymannian variance estimator that requires that something like that xi minus yi equal to constant for all I, which can be trusted, a bit trusted. So the next question is, can we estimate the variance unbiasedly under wider assumptions? And this is Neymannian estimator. Is basically that yiz minus yiz star is the same irrespective of I. And we have in matrix notation that comes down to equation 1. And we showed that under wide generality, we can estimate the variance unbiasedly under this condition, under condition 2, where Q is a matrix. What kind of matrix Q is? Compare these two matrices. Forget about the other things. The other things will be hard to explain in this limited time. Look at this matrix here. The existing theory dwells on this matrix I minus n inverse j, I minus n inverse j, and more precisely, the unified notation, instead of I minus n inverse j, we just multiply that by a scalar. Existing theory dwells on q equal to 1 by n minus 1. Just talk about the mathematics part here, which will be more of greater interest. I minus n inverse j. And we require that q times something has to be 0. Q times something has to be 0. As opposed to that, we bring another matrix. Mode. Can we get rid of this? Go full screen. Can we get rid of full screen? Oh, full screen. Okay. Let's say, remember, okay, this is the condition. More generally, we consider matrices of the form written near the bottom of this page. Qj0, J is a matrix of all ones. That means Qj0, I is the identity matrix, J is the matrix of all ones. Qj0 and Q has diagonal elements 1 by n square. This is the mathematical part here, 1 by n square. This is the general class of matrices. Now see, the conventional choice that corresponds to strict additivity considers this Q. Look at this matrix. Qj is 0, yes, I minus n inverse j has all rows from 0, so it is 0. What are the diagonal elements? I contributes 1, j contributes 1 by n. So I minus n inverse j contributes n minus 1 by n. Outside you have this n times n minus 1, so you get 1 by n square. The result is that you can make an unbiased estimation of variance provided that kind of orthogonality holds not just for this specific Q but for any Q that satisfies these conditions. And here a little reflection will show that this condition is milder than this condition provided rank Q is less than n minus 1. Then we get a milder condition. Rank Q is less than n minus 1. Because this covers all vectors, the common space of these covers all vectors that are orthogonal to the vector of all ones. And this can potentially cover a subclass of such vectors. Here lies a trick. So using such a Q, you can estimate the variance under milder conditions. So these implications are here. Unbiased variance estimation is possible under conditions milder than strict additivity, and indeed milder if rank Q is less than n minus 1. This is the mathematical part of the discussion. Then we give some examples for stratified sampling, for split plot sampling. Then comes what happens if these conditions don't hold, mild or strict additivity. Then there is a bias, and these are all conservative estimators. So the bias is non-negative. The question is, you use one estimator, some estimator, some assumption that keeps the bias small. The trouble is that the bias also involves the unknown parameters. So to control the bias, we can employ two conditions, two kinds of criteria. One is minimaxity. Minimaxity across spherical contours. This is very similar to what the people in experimental design do under the criterion known as E-optimality. So bias control, one approach is minimaxity, and there one can show that again that Neymannian, the traditional method, is the minimax one. This is the most stringent and gives maximum protection against the worst possible situation, provided there is some provided. What is that provided? Provided pi I z star greater than 0 for every I n. Note that I and k are different. That means, given any two units, if the probability that unit I receives treatment j and unit j receives treatment z star, if this probability is positive, then the minimax choice of Q is a traditional choice, no improvement. The point is that there are sampling designs that is again that motivated the present world where this condition doesn't hold. A clear example is the one that concerns the split plot design. And there the minimax choice of Q is entirely different. Let me give you one example. Minimax choice. We have to go to equation 3. This is a partition form of that. This is one, the whole I minus n inverse j. And a partition form thereof. This is equation 3. This is a partition form thereof. A block diagonal version of that Q. That is the minimax choice, not the whole of Q. Next question is, anyone who is familiar with statistical inference, the decision theoretic framework, will immediately say that, well, one criterion is to minimize, is to protect against the worst possible scenario, which brings in minimaxity. What about the average bias, the Bayesian perspective? Bayesian inspired perspective, not exactly Bayesian, Bayesian inspired perspective. Now average means we have to make again, we have to introduce some kind of assumption about the parameters, like the unknown quantities. For example, in Bayesian inference, take a simple example. Mu, say normal distribution. Mu is unknown, sigma is known. You want to make a Bayesian inference about mu. Then you have to assume a prior about mu, and you can of course talk about non-informative priors, but still the prior has to be assigned, and there is some element of subjectivity there. And the very purpose of doing these things by potential outcome models is to avoid assumptions. These are assumption-free results, almost assumption-free results. So, if we try to control the average bias, the bias depends on unknown parameters. So, the averaging has to be done with respect to those parameters using some kind of Bayesian type approach, which we call the superpopulation model. And many people in potential outcome, for example, Professor Rubin himself, doesn't like the idea, that some others did that. So we excluded this in our paper. But, well, I understand here many of you are interested in operations research, and this can lead to interesting problems in operations research. And, well, this also has an interface with operations research, bias control. Then minimizing average bias. Here I skipped all the details, but one can show that the results can be very different from those under minimaxity. Analytical solutions may not exist in general, and semi-definite programming formulation helps. What is semi-definite programming? In linear programming, you have variables x1, x2, xn, which are non-negative. In semi-definite programming, you replace these by matrices, which are non-negative definite, or positive semi-definite. And there are algorithms for semi-definite programming. This area will, I think, well, in MATLAB also these algorithms are available, and this area started gaining attention from the late 1990s, so a relatively new area. And then comes another question from comments, the concluding remarks. Case of treatments with factorial structure readily covered. Our results paved the way of exploring an optimal strategy. What is optimal strategy? We are talking about the inference procedure for a given method of partitioning. The partitioning, that means a given set of probabilities PT, the partitioning, together with a given estimator. What is the best combination of partitioning rule and estimator? This is called optimal strategy. And in the unified theory of surface sampling, such optimal strategies have received much attention, but again under Bayesian type assumptions, which are called superpopulation assumptions. Again, the proponents of potential outcome models may not be very happy with such assumptions, because a primary objective of this line of research is to make the work assumption free. So there is some debate about this, but mathematically this can be very interesting problems. And I'm sure these are publishable in good journals also. And then simple superpopulation models, standard techniques, simple superpopulation models, standard techniques of finite population sampling work. In the presence of such correlation, no correlation across units, then the directional derivative techniques can be useful. And with my teacher, Professor Sengupta, I did something in this direction way back, about 30 years back. It came out in biometric, and I believe such techniques would be useful here too. So with this, I conclude my talk. And before that, I must thank you for enduring me over the last 1 hour. Thanks so much for your patience. Thank you very much.
Any questions? Any questions from this side? So in that case, thank you very much.
Thank you once again.